objects with masses m1 and m2 separated by distance x is F equals g times m1 times m2 divided by x squared, where g is the gravitational constant. How much work is done by gravity when the separation changes from x1 to x2? Assume x2 is less than x1. First off, the column on the left is the problem worked out, the middle is the notes of how the problem was solved, and the far right is the definition of each variable involved. Now, if you recall from the lectures, the work equation is equal to the integral of the force equation. In this case, the work equation is equal to the integral of negative gravitational constant times mass 1 times mass 2 divided by x squared, with an upper bound of x2 and a lower bound of x1, as the separation distance is changing from x1 to x2. If you don't understand why force equation will have a negative sign, then allow me to explain. Attractive forces, such as gravitational force between two masses, will always have a negative sign, and so will m1 when being attracted to m2 and vice versa. The way that I like to think about it is as such. An object being attracted to another object via gravitational force is comparable to how the gravitational force put on a person, which will represent m1, by the Earth, which will represent m2, causes the person to accelerate towards the center of the Earth, which will give the person a negative acceleration value. If we were to plug that value into Newton's second law, then we'd get a negative force value. If you did think the force value to be positive, it's very likely because you were thinking of the values in solely a scalar sense instead of as a vector quantity. There may be other reasons, but I found that to be a notable possible reason to point out. So just to recap on a notable point, we should consider the mass as being attracted to the center of the other mass. I hope this was helpful in helping you to understand why we can consider the equation to have a negative sign. When we integrate by x, we get that the indefinite integral is negative 1 over x. After that, we have to finish the integration using the evaluation theorem in order to find the final equation for work. Once you do that, we get that the work equation equals negative 1 times gravitational constant times mass 1 times mass 2 times the difference between the inverse of x1 and the inverse of x2. We can cancel out the negative sign by simply turning the equation into gravitational constant times mass 1 times mass 2 times the difference between the inverse of x2 and the inverse of x1. As you may have noticed, the question said that x1 would be more than x2, but that means that the inverse of x2 will be bigger than the inverse of x1, which also means that the work value will be positive. If we were to integrate without the force equation having a negative sign, then the order of the inverse x's would be swapped, which would lead to a negative work value because we would be multiplying by a negative number, as the inverse of x1 minus the inverse of x2 would be a negative number. And since we know that the direction of the force vector is pointing in is the same direction that the position is changing in, we know that the work value is a positive value, which is what we will get when we use the following equation. And the equation is all we need to find for part A. If one mass is much greater than the other, the larger mass stays essentially at rest while the small mass moves toward it. Suppose a 1.5 times 10 to the 13 kilogram comet is passing the orbit of Mars, heading straight for the Sun at a speed of 3.5 times 10 to the 4 meters per second. What will its speed be when it crosses the orbit of Mercury? Astronomical data is given in the tables at the back of the book, and g equals 6.67 times 10 to the negative 11. To find the final velocity, we have to recognize that the total work value is equal to the change in kinetic energy, and the change in kinetic energy is equal to 1/2 times mass of the comet times final velocity squared minus 1/2 mass of the comet times initial velocity squared. To get final velocity alone, we have to multiply both 2 and m subscript 1 on both sides, which will cancel out the m subscript 1 variables and the 1/2s on the right side. After that, we add initial velocity squared to both sides, then we square root both sides to get the final equation. The square root of 2 times gravitational constant times mass of body 2 times the difference between the inverse of x2 and the inverse of x1 plus the final velocity squared. Here are all the variables that we're going to be using that are provided to us via the question or the data table mentioned. Feel free to pause the video for a moment to look at all the data. And you may be wondering why we're using the distance between the planets and the suns as the value of the distance between the comet and the suns. This will be because the comet will be in about the same area as the planets in those instances. So the comet will be at the same distance from the planet. So the comet will be in the same distance from the sun as the planets will be from the sun. So the distance between the planet and the sun will be valid for the value of the x variables. If you were to go by the textbook's word, then we'd get a final velocity of 6.8 times 10 to the 4th meters per second. If you got a different answer, it may be possible that you made a typo in the x variable, typed in an exponent incorrectly, or but those are just the possibilities that are at the top of my head. There may be a different reason. You may have seen a different form of the equation for work, but I guarantee you that I've attempted many other forms of the integral of the force equation and have gotten the same answer as shown on this slide. Here are the key learning points for you to look over. I hope this was very informative. Have a good day.